In this next section, we're going to be talking about probability. And we're going to begin with a introduction to the basics of probability that will help set you up for success later. And to begin here, we are going to talk about one of my favorite basketball players ever, Larry Bird. He played for the Boston Celtics in the 1980s and into the early 90s, and is generally considered to be one of the best basketball players ever. Now, one of the things that he was really good at was free throw shooting. And so what we have here is information from two different NBA seasons in terms of how good he was at shooting free throws. Now, if you're not familiar with a free throw in basketball, that's okay. The very basics of it is it's a shot that a player takes about 10 feet from the basket. And typically these shots come in pairs. So you have a first free throw attempt and then a second free throw attempt. There are other occasions during a basketball game where you could have just one free throw or maybe 3 free throws, but we're just going to concentrate on 2 free throws here. And so what we have here is what's called a contingency table that's summarizing the results of the first free throw attempt and the second free throw attempt jointly. So for example, 251 times Larry Bird made the first free throw and also made the second free throw. 34 times though, he made the first but missed the second. And if you were to add 251 to 34, you get 285. So 285 times he made that first free throw, where we don't care about what happened on the second free throw attempt. Notice 5 times Larry Bird actually missed both free throws. Okay, let me do some erasing here. So in this kind of a table, we typically think of this here as the body of the table, and sometimes you will only see a table with this corresponding information in it. That's still a contingency table. In this particular case, I also added a summary column and a summary row as well. Very often we refer to these as the margins of the table since they are on the ends of the table. Okay, so let's move on to page 2 here. Now, we will often want to define quantities like what we just saw in a more generic manner in terms of, let's let the letter A simply denote that the first free throw is made, and the letter B denote that the second free throw is made. In statistics, then, we call this A, this B, or the corresponding meanings for A and B for this particular example. We call these events. And the reason is because they define or they describe possible outcomes that could occur. Now, we can also talk about, well, what's the opposite of A and B? And in statistics, we have a name for that as well. They are called complements. And there's a variety of different ways to denote this. I'm going to use this notation here. A bar is the complement of A. And A bar in this particular case would be the first free throw is missed. B bar is going to denote that the second free throw is missed, and that is the opposite of B, the second free throw is made. So let's just make sure that I said that right here. A bar is first missed, and B bar equals second missed. Now, sometimes in other areas, you may see these complements denoted a different way. A with a superscript C, or A with a prime mark or a tick mark right next to it. We will use the bar notation, which is fairly common. So with this notation, then we can redefine our contingency table to simply look like this. And oftentimes when we are dealing with contingency tables, we're very interested in corresponding probabilities, such as what's the probability that Larry Bird will make the first free throw and make the second free throw as well. So to obtain these particular probabilities, what we can do is simply divide all the numbers that we saw in that contingency table by the total number of free throws attempted, which was 338, or total number of free throw pairs, that is. So in this particular case, this 0.7426 is equal to 251 divided by 338. Now over here on the margins of the table, what we have here is, well, regardless of what happened on the second attempt, what was the probability he made that first attempt? And in that particular case, that would be 285 divided by 338. Now notice right here in this table, we have the value of 1. Because if you remember in terms of the counts in the contingency table, we have 338 right there. So what this is basically doing is simply adding up all the corresponding probabilities in the table at that location. Also notice how it's adding up these probabilities on the margins as well. Okay? So also we can think of it this way, since the probability then is 1, then for that whole table there, this means each free throw pair has to fit in one and only one of these 4 cells in the main body of the table. Okay, so then symbolically then, we can write out probabilities in this form, and we will use this kind of a notation throughout our course, and it's standard notation that people use. We use a P, and then a parentheses, and parentheses, and then inside we put the event, and we phrase this as the probability the first was made, or more generically we can say the probability of A, and that was 0.8432, which was located right here in the table. We can also do the same thing for the probability of B, that's 0.8846. The probability of A complement is 0.1568. Again, the probability that Larry Bird missed that first free throw, where we don't care about what happened on the second. So I've used the word margins a few times already, and we can look at what are called marginal probabilities, which then represent, again, what's on the edges of the table. Sorry, I'm getting a little bit messy here. And we've already been working with them, I just hadn't called them that. So here are the marginal probabilities. Now what's interesting then is that if we were to take the probability of A plus the probability of A bar, the opposite of A, again, look what we get. It sums to 1. You can do the same thing for the probability of B as well. And the reason why I point this out is that this leads to a nice expression that we can often use or will come in handy to us. And that is, so the probability of A plus the probability of A bar is equal to 1. Well, if we did a little bit of algebra, we can now rewrite this as the probability of A is equal to 1 minus the probability of A bar, or the probability of A bar is equal to 1 minus the probability of A. Again, you'll see how this comes in handy in a number of different places throughout our course. Now, in terms of the body of the table, we can write out the probabilities in this form. The probability that the first was made and the second was made, we've already found that to be 0.7426. And this just represents a symbolic way to denote it. A general symbolic way is to use this notation. The probability of A, and then we have like an upside down U. This actually is the intersect symbol. The probability of A intersect B, meaning when they are both together, is 0.7426. Sometimes you'll see people extend over this and that we saw there as well. These probabilities like this, so we could also look at, let's say, the probability of A intersect B bar, probability of A bar intersect B, probability of A bar intersect B bar as well. These probabilities are called joint probabilities because they give us the probabilities of more than one event together. So as you will see here, I failed to mention this before, you see here there's a lot of text that is highlighted in blue. This corresponds to important terms that we will be using, and you do need to be prepared. You need to, or I should say, you need to understand what these terms are, be prepared to use them in a variety of different situations. Okay, so let's take a little bit of a closer look at this probability of A, the probability that the first was made. Now, let's see, how did that come about? Oh, actually, I'm going to go back up and do some more erasing. So here is the probability of A. That's simply adding the probability of A intersect B and adding the probability of A intersect B bar. And we get from that the probability of A. So that's can also be a very useful item to understand, that we can take this marginal probability, write it out in terms of some joint probabilities as well. And where that can be useful is in situations of, let's say I want the probability of A intersect B. I can also then write this as the probability of A minus the probability of A intersect B bar as well. Okay. Now, there may be times where you are interested in, rather than and, meaning A and B or A intersect B, you might be interested in probabilities associated with the probability of A or B occur. Where that or actually means either A occurs without B, either or. It's hard to say some of this stuff sometimes. This means A occurs or B occurs, or A and B occurs. Okay? And we can write this symbolically like this: the probability of A, and then this symbol looks like a U. Union B, union means essentially the word or. We can write out these kinds of probability statements in this form here. And what this means then, corresponding to what I just said, you are basically looking at, you want at least either A or B to occur. They both could occur, and that's fine. And so the probability that A union B is equal to 0.7426 plus 0.1006 plus 0.1420. So perhaps I should have wrote it like this. That would make it a little bit more clear. There we go. So this would go down to here. And let's wrap this all the way around to there. And so that's what this expression is. Now, excuse me. Now there's actually a little bit of a shortcut way to find that expression. And that is, what we can do is simply take the marginal probability for A plus the marginal probability for B, and then subtract out now the intersection between A and B. Well, why? Well, here's the probability of A. Here's the probability of B. And notice, to get the probability of A, we needed to add these two probabilities together. To get the probability of B, we need to add these two probabilities together. And look what happens. We've actually added in this probability of A intersect B twice. So because of that, we need to subtract it out once. And so that's how we find this probability of A union B. Now what you should do on your own is look at other situations, such as the probability of A union B bar. How would you find that? It's the same basic concept. Probability of A plus the probability of B bar minus the probability of A intersect B bar. And then also on your own, think of it in terms of the probability of A bar union B. Also find the probability of A bar union B bar. Make sure you can do that. Now, this general expression here, and I just want to make sure that this is clear. If I want to, I could put a bar on top of the A, and it's still meant to be the same generic expression, okay? Or I could put a bar on top of B too. I just need to do it wherever I see B. This is often, this expression here is often referred to as an addition rule for probabilities. Now also what this addition rule gives us is that we could rewrite it by using some simple algebra. Let me do some erasing again. I could take this probability of A intersect B, move it over to this side, so add probability A intersect B to both sides of the equation, and I could also take this right here and move it then back over to the other side. In other words, subtract the probability of A union B from both sides of the equation, and now I have a different way that I can represent the probability of A intersect B, which actually can be handy to have. Well, here's another way you can find this probability of A union B. Let's go back up to this table here. Now remember, in the body of the table here, all these probabilities will add to 1. And the probability of A union B is what's represented in yellow. Well, how about we just simply take 1 minus 0.0148? Well, then we will get the probabilities that are in yellow, since, again, these 4 cells of this table add up to 1. And so, in other words, what we're doing is using a complement, like what we saw earlier, but now with 2 events at exactly the same time. And so what ends up happening then is this probability of A union B is equal to 1 minus the probability of A union B, but look at this, we extend the complement all on the top. Well, what is then A union B with that line on the top? How can we actually express it? Well, what ends up happening is this. This A becomes a complement. This B becomes a complement. And then rather than having the union symbol there, we reverse it and make it the intersect symbol. This is often referred to as De Morgan's law, or one of his laws corresponding to probabilities. And again, the way to see that indeed that this expression is equivalent to this expression is just to simply go back to our contingency table that we see there. Okay. Another little definition that we need to understand is that there can be what are called mutually exclusive events. And from that name, mutually exclusive, hopefully you can see what that basically means. And that is, well, if A occurs, B cannot. If B occurs, A cannot. So in other words, the probability of A intersect B is equal to 0. So then I have a simple question here. Well, are A and A complement, or A bar, mutually exclusive? And the answer is yes, because one is the opposite of the other. They both can't occur at the same time. So if they could, that would be like saying Larry Bird both made and missed his first free throw. And that obviously can't occur. Okay, so let's move on to page 7. We're going to talk about conditional probabilities now. What a conditional probability is it's the probability that a particular event happens, given that I already know that another event has occurred. And so if we want to be very generic here, let's look at two possible events, A and B. And if I want to know what's the probability that A occurs given that B has already occurred, this is called a conditional probability. Symbolically, it's denoted like this, where we have the probability of A, then we have this vertical line here, which is worded as the word given. Probability of A given B. Well, what is this conditional probability then? Well, one can show that it's simply this. The probability of A intersect B divided by the probability of B, provided, of course, the probability of B does not equal 0. Now, where does this actual expression come from? Well, think of it this way. Suppose that we know that event B has occurred. Okay? Now what you're going to be doing is looking at, well, what's the probability that A occurs, given that I know that B occurs already? The probability of A intersect B has to be less than or equal to, the probability of B, because B is here and B is there. Okay? So essentially what you're doing is you're looking at, well, what proportion then is this probability of A intersect B in comparison to probability of B? Or in other words, how often does A occur given that B has already occurred? In terms of what happens, or what's the probability that they jointly occur together, given that I know that B has already occurred? Okay, so let's take a look at some other ways to express this. So what I could do is multiply both sides by the probability of B, and look what happens. That probability of B is going to come over to the left side, and so now we have this particular expression here. The probability of A intersect B is equal to the probability of A given B times the probability of B. So now we have another way that we can find this joint probability. So on a test or some other way for me to grade you, I might ask you to give me a few different expressions for how we can actually find the probability of A intersect B. This expression then, the second expression here, is often referred to as the multiplicative rule. Now, one can also write conditional probabilities looking at, given A, what's the probability of B as well. And as you might expect, the same things occur. The probability of B given A is equal to that joint probability again, but now it's divided by the probability of A. So we're looking at, well, what proportion of time does B occur, given that I already know that A occurs? Okay, so let's go back to the Larry Bird example. And so what I have here is these tables of these probabilities that we've seen before. And what we're going to be looking at is the probability that the second free throw is made given the first is missed. At least for basketball fans, this is a very important probability to look at. In general, one may think that when a basketball player misses that first free throw, that perhaps that basketball player gets down on themselves. They maybe psych themselves out, and that will lower their probability of making that second free throw. And so perhaps then the probability of making that second free throw, given that the first is missed, is going to be less than, let's say, maybe instead the player had made the first free throw That gave that player a lot of confidence, and so then when they did that second free throw, they might be more likely to make it then. That's often a way that a lot of basketball fans think about it. Alternatively, another way to think about it is, let's say that that basketball player misses that first free throw. Rather than getting down on himself or herself, we're talking about women's basketball too, rather than getting down on themselves, what could happen is that now that basketball player is going to be really concentrating on that second free throw, and they're going to make sure that they're using the correct form when they take their shot. And therefore, maybe they will have a higher probability of making that second free throw than if they would have made that first free throw to begin with. Okay, so let's take a look at this probability then. So the probability the first is missed and the second is made is right here, 0.142. And we're going to be looking at, well, how does that correspond to the probability if you just missed that first free throw where you don't care what happened on the second? And so we can see that that 0.1420 is a big part of the probability that the first was missed. And so the probability of the second was made given the first was missed is 0.9057. Turn the page here. So we're on page 9. Now we could rewrite this in terms of A's and B's as well, and that's what I did here. Now, on your own, I want you to verify that the probability of second made, given that the first was made, was 0.8807. So, in fact, look at this right here. This is actually less than if Larry Bird had missed that first free throw. So, perhaps in Larry Bird's situation, he does concentrate more on making that second free throw, making sure he's using the correct technique, supposedly, or perhaps I should say. And that leads to a higher probability of making that second free throw. But in the end, what we're actually dealing here with is just a sample. And these two values are quite close to one another. And so later in this course, what we will do is now take into account that this is just a sample. And based upon the sample, make a judgment regarding, let's say, all of Larry Bird's free throws during his career, or let's say if he was kept on playing, and we can make a judgment of, well, does it matter what happens on that first free throw for Larry Bird? So stay tuned. We'll take a look at that more later. Okay, so let's move on to a new example dealing with conditional probabilities. This doesn't deal with contingency tables. And this deals with the TV game show, The Price is Right. For those of you who are not familiar with this game show has been on since about 1970 on TV. It's usually on about 10 a.m. Mondays through Fridays on CBS here in the U.S. And the way this game works is as follows. You have 3 contestants that are trying to win the game. And the way that you win the game is that you spin this big wheel that has values of 5 cents, 10 cents, 15 cents, all the way up to $1 on it. And the contestant that is closest to $1 from one spin or through adding or the combination of 2 spins wins this particular game. Okay? And so let's take a look at the game in action. So here I have a little YouTube video that I found on the web that shows this game being played, and we'll just watch a small segment of it.
Price is Right. Time to spin the wheel. Wilbert, start us out. Start us out. Go ahead. Wilbert.
So there's the big wheel. He's going to spin it.
Who do you want to say hi to?
And he hopes
I want
to
to say
get
hi
as
to
close
all
again
my
to
family, friends in
$1
California,
as
New Jersey,
possible, one
and
or a
Florida.
combination of two
Everybody,
spins.
remember, if you get $1, it's $10,000.
On the first spin, he gets 25 cents. He needs to make a decision. Should I try to do that second
75
spin?
or less.
Something I failed to tell you is
75 or
that
less.
with this second spin,
75
when
or
you
less.
add that amount to that 25
There's
cents,
your
if it goes over the $1, you automatically
There's
lose.
your 75. That was a good spin,
And
buddy.
so that's why you
Set
have
that
to
wheel
be
going,
careful.
man.
And it's actually a decision you have to make. Should I take that second
Come on,
spin or
75
Oh,
not?
for 10.
And let's just see what happens here.
$10,000.
And he gets 75 cents. So 75 plus 25 cents is $1. He's going wild because he gets a little bit of a bonus for getting $1. In fact, he gets $10,000. So he's quite happy. And now these other two contestants are going to try
Charlotte,
to
go get another 10 grand.
and then if they do, they can they have like a what's called a spin-off where they try to break the tie. I won't go through showing you what happens, but I will tell you, as you can see here on the title of this YouTube video, this is the craziest Price is Right wheel spin ever. So take a look at it on your own if you're interested. Now, I've always been a big fan of the Price is Right because of I want to be able to come up with the optimal strategy to play a game. After all, I'm a statistician. I deal with probabilities all the time. I want to try to use my knowledge of probabilities to win that game. And a number of years ago, there was a nice paper that came out in American Statistician that looked at what's the optimal way to play this game on The Price is Right. And this paper looked at it in terms of conditional probabilities. So that first contestant, or the first person that's spinning that big wheel, let's say they got 5 cents on their first spin and they need to make a judgment. Well, do I stop or do I spin again? Well, if they stopped, notice we're doing a conditional probability here. The probability that they win, given that they stopped at 5 cents, is extremely small, 0.0034. But if they were to spin again, given that they did that, the probability that they would win goes up to about 0.21. So since 0.21 is greater than 0.0034, the optimal strategy to play in this particular situation, if you get 5 cents on that first spin, is to spin again. Take that second spin. And so let's look through this table here. Let's look at 50 cents. So let's say you got 50 cents on that first spin. Now you're halfway there to $1. So you might be thinking, well, the probability of winning is probably going to be about equal. But in fact, that's not true. So given that they got 50 cents on that first spin, and they decided to only spin once, they didn't take that second spin, the probability of winning is only 0.0574. Why? Well, remember there's 2 other contestants that still have to spin. But if they would have took that second spin, now the probability is 0.19681. So again, the optimal strategy is to take that second spin if you started with 50 cents on that first spin. So where's then the cutoff between I should take the second spin or stay? Don't do that second spin. Just stay on that what you had on that first spin. Just take that. Well, it actually ends up occurring right about 65 cents. At 65 cents on that first spin, you should still spin again. That's going to give you a higher probability of winning. But at now 70 cents, that's when the probabilities or that inequality sign changes. Now with 70 cents, you should stop. You should stay because the probability of winning is higher if you just did that one spin. So if you're ever on The Price is Right, that will give you a way to optimally play that game. And I have to admit that I've actually tried to get on The Price is Right. Here I am. This is a screen capture from the the broadcast of the TV show from a number of years ago. Here I am in the audience, and here's my wife, Kim. And the way that they choose contestants to play their games is that they ask audience members to come on down, essentially to the stage, to play the game. Now, unfortunately, I was not asked to come on down. Perhaps they knew I was a statistician, and they realized that I knew how to play their games in order to maximize the probability I was going to win. Anyway, so I wasn't chosen. Now, what if, now we're leaving that example, what if there are more than 2 events? And let's just call them, let's say, A1, A2, down to AK, just to be generic. Well, we could write out the probability of A1 intersect A2, just like what we've done before, using that multiplicative rule, probability of A1 times the probability of A2 given A1, or you could say the probability of A2 times the probability of A1 given A2 as well. But what happens is now there's three events, and we're looking at the joint probability, or the joint, look at the probability of the joint intersection between these 3 events. Well, how about we just think of this part right here with A2 intersect A3 as, let's say, B. And we would simply write that out as the probability of A1 intersect B, which is the probability of A1 times the probability of B given A1. Well, just write out what that B is then, and that's how you get that expression. But we can go further. Let me erase this. So now let's try to break this up here. And let me come down here to an empty spot. If I just had probability of A2 intersect A3, I could write that out as a probability of A2 times the probability of A3 given A2. Okay, you could write it out like that, but remember now we are actually conditioning on A1 as well. So now here I put in A1, and also I have A2 intersect A1 there. Sorry, I went off the screen. And you can keep on doing that for more events, 4 events, 5 events, and you can write out the general expressions then what these large joint probabilities would be. Okay, let's talk about another concept with probabilities that's very important, and that is independence. Suppose I have 2 events, again, A and B. They are independent if the probability of A given B is equal to the probability of A. Or you can think of it also, excuse me, equivalently as the probability of B given A is equal to the probability of B. Well, why? Well, think of it this way. I don't care if B occurred or not. Probability of A is still going to be the same. Thus, A and B are independent. That's the way to think about independence here. Now, this also then leads to a nice way to express the probability of A intersect B. And this is provided that independence is true. We can now write it out as the probability of A times the probability of B, a lot more simply. Make sure that you can mathematically actually show that that is true. And if you can't, you need to ask me a question. Now, there's another way that you can actually check for independence as well in terms of a contingency table structure. So we can write our contingency table out. Oops, not sure why I had such a thick red pen there. We can write our contingency table out so that now it represents conditional probabilities. And if we have equality of these conditional probabilities across the columns, then we have independence. Well, why? Well, remember, if probability of A given B, if we have independence, the probability of A given B is equal to the probability of A, and the probability of A given B complement then would also be equal to the probability of A if we have independence. And so that's why that occurs. Now we could also rewrite this then in terms of probabilities of B given A or A complement as well. or also with the B complement too. And now in this particular case, we have independence if we have equality across the rows. Note that in a simple 2x2 table setting such as this, if you have one, you're going to have the other as well. Okay, so let's look back at the Larry Bird example once again. Do we have independence? Well, first of all, what we could do is we take a look at the probability of second made given first is missed. It was 0.9057. And if we go back to our table, we see the probability of second made is 0.8846. So therefore, we do not have independence. In other words, we have dependence. But notice how close they are, and referred to our discussion before with respect to how this is a sample, and then later in the semester we will look at it from the point of view of trying to generalize to a population. One could also then compare the probability that the second is made given first is made. Compare that to 0.9057 as well. You're going to see that they are close, but they're not exactly. So at least in the sample itself, we do have dependence. And as I say there, in capital letters, independence will be very important to us in our course. So let's take a look at another application of conditional probabilities. This is now with respect to something that's called Bayes' formula. And Bayes' formula basically allows you to calculate a conditional probability with the help of other conditional probabilities. This is widely used in an area of statistics called Bayesian analysis. Here we're just going to look at the most basic aspects of it. So again, let's say that we have two events, A and B. Of course, we have their corresponding complements as well. Then we can write out the probability of A given B is equal to the probability of B given A times the probability of A, all over the exact same thing in the denominator, plus now the probability of B given A complement times the probability of A complement. Well, from an initial look here, you might be thinking, well, why? Where does that come from? Well, it all comes back to this original expression that we had before for the probability of A given B. Let me do some erasing here. Now remember that this numerator here can actually be written out by the multiplicative rule as the probability of B given A times the probability of A. Okay, so that's how we get this numerator. Now to get the denominator here of our expression, how is probability of B equal to that? Well, this comes down to what we had talked about towards the beginning of this section, and that is we could write out a marginal probability as the sum of its intersection with A and A complement as well. We actually were writing out, I think, in terms of probability of A is equal to the probability of A intersect B plus the probability of A intersect B complement. I think that's how we wrote it out instead. If you just flip the letters, you get the same, you can write it out in that way as well. And so that's where this expression comes from. Again, on a test, I might ask you, well, show me how you can get from here to the Bayes formula expression above. Now there's actually even a more general representation of Bayes' formula. Let's say if we have K different A events and M different B events, then we have a nice little extension to this multi-event setting using the same basic ideas that I just showed you. So where is this important? Well, one place is with respect to doing testing for infectious diseases. So now we are on page 16. Part of my research involves trying to test for infectious diseases more efficiently. And so I often work with this Bayes formula for that process. And unfortunately with infectious disease testing, most diagnostic tests are not 100% accurate. If you ever heard of an expression like a false negative or a false positive, well, that's what happens with infectious disease testing. What we hope is that those probabilities of having a false negative or false positive are small. And I guess I should back up. What does a false positive mean? Well, perhaps maybe you've been tested for a disease, it comes back positive, but in fact you're truly negative. Now, a false negative would be you're tested for a disease and it comes back negative, but truly you're actually positive. And so we want the probabilities that those errors occur, we want those probabilities to be really small when developing an infectious disease test. So let's talk about this with respect to HIV testing. Suppose a clinical trial is being conducted on a new HIV test. And what we want to do with this new HIV test is hopefully minimize the probabilities of having these false positives and false negatives. And so let's say we have a table like what we've seen previously, where we have the HIV test results as either negative or positive on the columns. And on the rows, we have a way, let's say, to actually determine does someone truly have HIV? Yes or no. Okay. Ideally, if the answer is no, they don't have it truly, we hope the test comes back negative, so we have a correct result. Or if a person is unfortunately truly has HIV, we want that test to come back positive, and so again we have a correct response. Now, what we see here also is these false positives and false negatives as well, which again we want to minimize the probabilities that those occur. So statisticians, epidemiologists, physicians are all interested in probabilities corresponding to that table that I just showed you, relative to conditional probabilities. So one of the probabilities that they're interested in is something called a sensitivity, where the sensitivity is the probability that you test positive, but you are actually truly positive. We want this to be as high as possible. So given that you truly have it, we want the probability that the test detects it to be as high as possible. Also, with respect to there's something called a specificity, which is exactly the same as the sensitivity, but now we are talking about a negative test, or you are truly negative. Now we can turn things around as well. So instead of having the actual result as what's being conditioned on, you could put that into that's what you want the probability of, now conditioned on the test result. With that, then, you get what are called predictive values. So the positive predictive value, meaning given that the test is positive, what is the actual probability that someone truly has that disease? The negative predictive probability is the same thing, but now you're talking about negatives and no, you don't have the disease. Again, we want these probabilities to be as high as possible. Well, let's look at this a little bit more closely with some actual information. So a paper that I actually I used for a recent paper of mine that I wrote was this paper by Branson et al. In 2014. And in this work, what they do is they look at about information from about 30 different other papers that evaluate a variety of different HIV tests. And what they found as the observed sensitivities for those tests were somewhere between about 96.3% and 100%. The observed specificities were between about 99% and 100%. Again, we would like these to be as close to 100% as possible. So let's say that an HIV test has a sensitivity of 0.993 and a specificity of 0.999. Excuse me. Well, what's the probability of then coming up with these false positives or false negatives? So let's say that someone is truly has HIV. What's the probability that the test would unfortunately say that they are negative? Well, this is where then the complement comes into play. So we take 1 minus 0.993, because the sensitivity, that aspect, what's inside the probability statement, gives us what we need. and we get 0.007. Now, for the probability the test is positive, given that the actual is no, I want you to find that on your own. It's not too difficult. If you have a question, though, let me know. And all this is doing is working with complements, but complements written in terms of now these conditional probabilities. So in the past, we saw like the probability of A is equal to 1 minus the probability of A complement. Well, what we could do is simply stick in a given B on both sides. Okay? Excuse me. Now, some recent HIV prevalence estimate in the United States that was given by the CDC was 0.004. Well, what does that mean? That means the probability that the actual is yes is 0.004. Or in other words, if you have 10 million people, you would expect about 40,000 people to be to have HIV. But what's the positive predictive value in this situation? And the reason why I bring this up is as follows. Imagine that you have been tested for an infectious disease. Could be HIV, could be something else. You're, let's say, in the examination room of your doctor. Your doctor walks in and says, "Okay, I have the test results, and I'm sorry to report that the test was positive." Well, what's the first question then that you should ask then that doctor? Well, you should ask, what's the positive predictive value? In other words, what you really want to know is this. Given that I tested positive, what's the probability that I truly do have the disease? So how would we find that then in this kind of a situation? Well, this is where Bayes' rule comes into play. So let me actually copy and paste that from before. Okay, so there's where what Bayes' rule was. So what we could do now is think of actual is yes, test is positive as B. Okay. Now we know the probability of A. The probability actual is yes. It's 0.004 based upon this information from the CDC. We also know the probability of B given A, which would be the sensitivity, 0.993. Using that information, then we can also put that same stuff down below. Now, the probability of A complement, of course, would be 1 minus that 0.004. And the probability of B given A complement now would be 1 minus the probability of B complement given A complement. In other words, A complement again would be actual is no. B complement would be test is negative. So in other words, we're working now with the specificity. You plug that all in there and you get 0.9755 as the final answer. So if this unfortunately would occur, there's a good chance that you truly are positive for HIV. We can also then look at the negative predictive value as well. And that comes to be 0.999719, so quite high. So for that first question, we've already done that, and we've essentially already done kind of did the second. I'll let you look at that more on your own. Now, let me also get that back. Oops, excuse me. Let's look at a different scenario. Suppose there's a very rare disease out there. So now the probability is 0.00025 of actual yes. What happens now to these positive predictive values, these negative predictive values? Positive predictive value, look at that. It's 0.2. Wow. So in that kind of a situation, then, if you're in the doctor's examination room, you would want to explore further to confirm if then the corresponding diagnosis given is actually correct. Okay. looking at these kinds of probabilities, sensitivities, specificities, predicted values are actually kind of fun to do. And in fact, in some courses, you spend a lot more time talking about those as well. There's actually something called a receiver and operating characteristic curve that can be used to help decide how do you make a threshold to determine that someone's positive or negative based upon, let's say, some kind of continuous measurement like viral load that's being detected by a diagnostic test. I won't get into that here. There's other courses that you can take that we'll go into further. So that's the end of this introduction to probability.